Okay, so let's come back to this. I have given you U and V, all right? And theoretically, because of what I told you here, the vectors should be opposite of each other. And then what's going to happen to the magnitude? Well, the magnitude is the norm of the first times the norm of the second times the sine of the angle. So that should not change, right? So we should get, when you do V cross U and U cross V, I should get something that's opposite from each other. Same length. All right, let's see. When you do this, I'm not going to write down all the details here, but here you get 2 minus 1, right? And then for the next one, it's negative of 0 minus negative 1, right? Where do you see that? It's 0, 2 times 1 times negative 1. So negative of negative 1. You see where the negative signs are all over the place here? And then the third, is going to be 0 minus negative 1 again. All right, so the answer to this question is 1, and then negative 1, that's negative 1, and then negative 1, which is 1. Okay, so did you get this? I hope you did. The answer to that question I gave you is 1, negative 1, 1. Now, if you switch the order, V cross U, this will be, well, it's 1 minus 2, so that's 1 minus 2. And you don't have to write all the details down here when you do these things. And by the way, after a while, you can even just not write IJK, and you can sort of look, at the last 2 rows and then try to figure these things out. The second one, it's negative of negative 1 minus 0, right? Because 2 times 0 is 0, right? Remember, you have the negative sign because it's the second coordinate. The last one is negative 1 times 1, that's negative 1, minus 2 times 0, which is 0. So the answer to this question, V cross U, should be negative 1 and negative of negative 1, which is positive 1, and then negative 1. Okay, so I hope the negative signs did not confuse you. You will need to practice this a little bit. And you notice here, these are exactly the opposite, right? So you will find, and of course, it's pretty clear by now that V cross U should be the negative of U cross V. All right, some interesting things about the standard unit vectors, I, J, and K. I is 1, 0, 0, J is 0, 1, 0, and K is 0, 0, 1. If you do I cross J, and you can verify this on your own, or you can just look at this and imagine you have, I, J, K here, and try to, do this 3 by 3 matrix here. You don't have to do this. I mean, I don't think you actually need to write these things at this point. But you would notice here, this will be 0. No, sorry. What is I cross J? It'll be 0 for the first one because it's 0, 0 minus 0, 1. For the second coordinate, it'll be negative of 1, 0 minus 0, 0. That's still 0. Last one, 1, 1 minus 0, 0, which is 1. Okay, that's K. All right, so I cross J is K. And how about J cross K? All right, J cross K, it looks like it's 1, 1 minus 0, 0. And the other ones are always just going to be 0, just because there are so many zeros. And that's just I, right? And if you want to write K cross I, it's hard to do here. Maybe I should write I again here, 1, 0, 0. So you can visually do this calculation, right? And if you do that, it's going to be 0. And then the next one will be 0, 0 minus 1, 1. But then there's a negative sign, so it'll be 1. And then you have 0, 0 minus 0, 1, which is 0. When I say 0, 1, I mean, 0 times 1, right? But anyway, this is known as J. All right, so there's a little cycle. And should I do this clockwise or counterclockwise? I don't know which one is best. It doesn't matter, I guess, right? But I'll do a clockwise thing. I times J is going to be K. Okay, that's what the first one says. J times K is I. And K times I is equal to J. So you have this sort of the cycle of 3 standard unit vectors in 3-dimensional space. And by the way, if you go the other way, for instance, J cross I is what? Well, it's the opposite of this. That's going to be negative k, right? And then I cross k is going to be negative j and so on. And you can, figure this out. You'll not be using this very often, but it is something to remember. Okay, so these are, when I list these as notes, points to remember, but these are actually theorems. And I hope you know by this time what the word theorem is. It's different from the word theory. Theory is something that, people have come up with and many people agree. They are probably true. The theory of this and the theory of this. In mathematics, the word theory has to do with the body of the branch of mathematics. You can talk about, for instance, a matrix theory or theory of functions or whatever. But the word theorem is something entirely different. It's a statement that is proved to be true, or that has been proved to be true from axioms and definitions and other theorems. So there's no dispute that these are correct. These are correct, and somebody has given proofs, although you may or may not have seen this, and the proof could be quite messy, like in this case. V cross U is negative U cross V. Okay, and you have discussed that. Now, what is U cross V plus, U cross, it should be V. U cross V plus W. Well, can you actually do distribute? Is the distributive property still applicable? And the answer is yes. Again, this is hard to, well, it's not hard, it's just messy to prove simply because the definition of the cross product is very, messy, like complicated, but it is not that difficult to prove the distributive property. If you have C times U cross V, think in terms of what happens with the matrix, the 3×3, the determinant of a 3×3 matrix. This is the same thing as if C was in the second column, or it's okay if you sort of insert C in the third column, right? So it's still going to be that. So again, C can move around wherever you want that to be. Okay, what is U cross 0, right? And the answer, I mean, if one row is completely 0, of course you can see this is going to be 0, right? And if you are happy with this, something is wrong. You are not paying attention. Why not? Well, as you can see, the cross product is what? It's not a plant, it's an animal, right? No, it's a vector, all right? So you have to have the vector notation here. U cross U, that's an interesting one. What is U cross U? Is that U square? Remember, there is no such thing as a vector square, but U cross U is, and it may be surprising, it may not be surprising. It's actually 0, right? Second row, if the second row and the third row are exactly the same, then the determinant of that matrix will be 0. And so every entry is 0, so that's a 0 vector. And in fact, U cross V is 0 if and only if what? If one is the scalar product of the other, right? So that is, in other words, if U is parallel to V. Okay, there are different ways to think about this. Okay, so for instance, if you have I, J, K, and if you have this, and if the third one is a scalar product of the second row, these are called linearly dependent vectors. And whenever you have linearly dependent vectors, the determinant is going to be 0. That's one way to think about this. The other is, if you just go ahead and calculate, each of the 3 coordinates of this cross product. If one is, like, let's say ABC, and if the next one is KA, KB, KC, you can verify that each coordinate will be 0. Another way to think about this is, remember, this is supposed to be, what is that? The magnitude of this is supposed to be the area of the parallelogram. If the area of the parallelogram is 0, then what is happening? Well, these should be collapsing, because this gets smaller and smaller, and the only way that the parallelogram collapses is if one is right on top of the other one. And so that's another way of thinking about that. All right, so keep this in mind, and I will now define the last part of this section, which is, and this section is not very long, not like the last one or the next section, which is very long, but triple scalar product is the last thing we should consider in this section. What is the triple scalar product? Okay, well, so to illustrate this, let me give you three vectors, u, v, and w, all in 3 dimensions. And I want you to multiply or to take the cross product of the last two, v and w. Sounds like a German car, VW. And if you do this, all right, so what do you get? It's 3 minus, and I'm going to write down the answer here, all right? 3 minus 0, that's 3. For the next one, it's negative of, keep that negative sign, 0 minus 0, negative 0, which is the same thing as 0. And then the last one is 0 minus 1. You see the my points going here, 0 minus 1, so it's negative 1, right? So it's 3, 0, negative 1. Now, let's try to take the dot product. Okay, keep this in mind. We're taking the dot product of u with the cross product of v and w. So u dot v cross w. This will be the definition of the triple scalar product of u, v, and w. But this will be negative 1, 1, 2, dotted with 3, 0, negative 1, right? Okay, so what is that? Well, that's negative. Oh, by the way, as soon as you write this, for instance, you're in the wrong path. Why do I not even want to start my answer with a bracket? Because the answer is not a vector, right? So, and I often make this mistake, like, whoops, you see that error here? Yeah, I've already made a mistake, even before calculation. As soon as I say the dot product is, and if I write the vector notation, I'm on the wrong path. I need to stop that. All right, so this is negative 3 plus 0 minus 2, and this is negative 5. And that is a triple scalar product of these. Okay, so the triple scalar product I will define in a moment is u dot v cross w, okay, where you do the cross product first. But try to see how this is related to the 3 by 3 matrix when I have u as my first row, v as my second row, and w as my third row. You remember how you take the determinant of this 3 by 3 matrix using the first row as the basis of your row, the cofactor expansion. When you do this, you have negative 1 times 1, 3 minus 0, 1, and then negative of 1 times 0, 3 minus 0, 0, 0, 1, plus 2 times the determinant of this 2 by 2 matrix, which is 0, 1 minus 1, 1. And so this is negative 1 times 3. Let's just go ahead and write the answer here. Oh, you know what? Let's go ahead and try to show this. Negative 1 times 3 minus, this would be 1 times 0, and then plus 2 times negative 1. Okay. And I hope you are seeing all these numbers here, okay? Because what you see up here is negative 1 times 3, that's this one. And then 1 times 0, that's this one, that's negative of that. I really should be, yeah, I think that's okay because of 0 here, yeah. Okay, and then the last one, 2 times negative 1, right? And so that is negative 5. What I'm trying to say is that the triple scalar product is nothing more than the determinant of this 3 by 3 matrix, okay? And so I'm going to tell you what's so important about this. But yeah, so let me just go ahead and give you the definition. Okay, so here's the definition, the formal definition, which I have been referring to. But the scalar, by the way, sometimes people call this scalar triple product. This book called this the triple scalar product. So I will go with that, a triple scalar product of three-dimensional vectors. U, V, and W is as follows. It's basically U dot V cross W. Now, does this even make sense? Okay, because sometimes people write things that, things don't make sense. V cross W is a vector, right? So it's okay to have a dot product of a vector and a vector. The answer is going to be a scalar, a number, okay? You couldn't, for instance, say u dot v dot w, because that would not make sense, right? So that's a scalar. And of course, the scalar is a number which represents something, okay? Now, I want you to take the same thing in here. What I have is u, okay? Try to use these u, v, and w. And I want you to calculate, as I pause this and as I conclude the second part of this, before you go to the third part, I want you to calculate w dot u cross v, which is quite different from this, right? Because the dot product, I mean, w was not a part of the dot product here. It is here. And then go ahead and do v dot w cross u. Now, you may think this is very strange, okay? And see what you can come up with, all right? And once you are done with these two scalar triple products, you come back and I will conclude this section.